Our speaker today, we're fortunate to have Don Lowe from Stanford University, the Department of Geological and Environmental Sciences. Don got his BS in geology at Stanford and his PhD at the University of Illinois, then came back to the USGS in Menlo Park for a postdoc before joining the faculty of the Department of Geology at Louisiana State University. And then in the late 80s, moved back to Stanford, where he is now a professor. Professor Lowe's research and influence in geology have been quite wide-ranging, and today he'll address for us the question, did the late heavy bombardment end not with a bang but a whimper? Evidence from 3.5 to 3.2 billion year old rocks in Archean Barberton region of South Africa.
Alrighty. Thanks a lot, Josh. Let me warn everyone ahead of time that this is a new talk that I actually prepared for this session. I was talking to Janice Bishop here just a moment ago, and she asked, oh, you've probably got this down pat, so, a canned talk. And I said, unfortunately not. So I warn you, there may be some rough edges here. But this is an area of great interest that my colleagues and I have been working on over the last 15 or 20 years. And we're sort of finally coming to fruition with some of the conclusions, I think, that we can reach. I might retitle this talk, if I had an opportunity, to something like this, and that is, when did the large-scale meteorite bombardment of the Earth decline to present-day low level? And that's really what I'm going to talk about here. Just who am I? I'm a sedimentary geologist. I'm going to show you some geochemical diagrams, but I sort of draw those in from outer space and really don't understand what they say. I'm a sedimentary geologist. I work out in the field a lot in rocks of various ages, primarily on sediment gravity flows, things like turbidites and debris flows and things like this in relatively young rocks, and then surface environments and life on the Archean Earth. And that's what takes me back to South Africa and other places virtually every year. And in fact, 1 week from today, I'll, at this very moment, be on a plane heading for Atlanta and going on to South Africa for about 3 weeks of field work. Most of the Archean work I've done over the last 30 years, and that of my students, is focused on these very old 3.55 to 3.2 billion year old rocks of the Barberton Greenstone Belt in South Africa. Now, can everyone hear me in the back and stuff? Good, okay. I have to acknowledge quite a number of people who've helped us out in our studies. My field colleague, Gary Byerly, an igneous petrologist from LSU. A student, Alexandra Kroll-Devatzis, who did an excellent study of some of the layers I'm going to talk about. And then a number of people who've assisted primarily in the realm of geochemistry. Okay, here we are. Geologic time. From present to back about when the Earth formed. The rocks we're talking about are this group of rocks right in here. They're Greenstone Belt sequences, that is, volcanic and sedimentary sequences. These yellow bars denote the time range of some of the earliest continental crustal sedimentary sequences, that is, rocks deposited on top of continental crust. And you'll notice that back in the early history of the Earth, we have a variety of sediments, but none of it represents materials deposited on the continental crust. All represents materials in the Greenstone belts. Here is roughly the range of late heavy bombardment, and you can see we're 500 million years to 300 million years after the end of late heavy bombardment in terms of this rock sequence. It outcrops right here. It's just a very small area in the eastern part of this Kafel Craton in South Africa. The age of the assembly and stabilization of this continental block is about 3.1 billion years. So we're looking, this combined with the Pilbara block in Western Australia, represent the oldest well-preserved sedimentary and volcanic sequences on Earth. You can go back to West Greenland and some older spots, but those rocks have been cooked, metamorphosed, and are very difficult to study as sediments other than geochemically. And a lot of what one pulls out of those rocks turns out to be quite controversial because of the alteration, metamorphism that they've suffered. Just a map of the Barberton Greenstone Belt. Main thing to draw from this, it's not very big. 20 kilometers is here. These gray areas are the mafic and ultramafic volcanic rock sequences. The yellow and brown are the sedimentary layers. And this is really just a window because all of this red, bright red, are younger granitoid batholiths that represent the last stages of stabilization of this continental block. So we're peering through these younger batholithic sheets into the older rocks beneath. Here's some younger late Archean sedimentary units. So we've got a window here back into the earliest part of the preserved geologic history of the Earth, and that's what we've been trying to exploit to understand what the early surface and ocean and atmosphere and life were like. I always like to tell people there's no easy way to pull information out of these rocks. I wish there were a place we could go to study greenstone belts like the Greenstone Preparatory School, but unfortunately the Greenstone Preparatory School doesn't teach about greenstone belts, but we thought it made a nice picture. The generalized stratigraphy of the Barberton Belt shows about 10 to 15 kilometers of section, most of it down here all the way up to this point. This is a section of mafic and ultramafic volcanic rocks. A few felsic volcanic units shown in here in sort of a light tan color, but the bulk of the sequence is made up of these light mauve and purple rocks, and those are the mafic to ultramafic lavas. The dark purple is the ultramafic rocks, and the lighter ones here are the basalts. And then at this point, it became an orogenic belt, lots of deformation, uplift, and erosion to deposit a thick clastic sequence at the top. And sometime after this point, there were the granitoids intruded, and it became a continental block. Another thing to note is there's a lot of time involved here. Okay? Here we're at 3547. The inception of orogenesis was about 3260. So we're running about 300 million years of history here, during which it was simply a volcanic province, no deformation, no orogenesis, and that's reflected in the lack of clastic sediments, essentially. And then it became a clastic sequence for maybe as long as 80, 90, 100 million years before the cessation of accumulation. The stratigraphy is actually more complex on a regional basis. We can divide it up into a number of terrains or provinces, but we can find similar units in all of these, and so we suspect that they accumulated fairly close together. If we look down at the lower part of the section, that's mafic and ultramafic volcanic sequence, you really see stunningly preserved volcanic and sedimentary features. I mean, if we didn't have ages on these, we could probably go out and claim they'd be Miocene in age and wouldn't have any trouble convincing people that that's the case. So we're looking here at pillows that have variolitic structures in them, nice pillows with radial pipe vesicles, pillows weathering out in 3D. Again, these are about 3.4 to 3.5 billion years old. The general picture of the development of this volcanic sequence is through fissure eruptions, generating low relief surfaces flowing out as lava rivers. Komatiites have about the viscosity of water. So you can imagine that they formed surfaces that were pretty flat. And so we suspect that the surface of these volcanic platforms, as we call them, were very flat, low relief. And of course, that's also reflected in the fact that between volcanic eruptions, there's no sign of any erosion taking place. There are no clastic material being eroded from these surfaces to produce any sorts of sands or gravels. Between episodes of volcanism, the platforms subsided and were covered by marine environments. And these periods of quiescence are marked by the accumulation of these little black units. These are cherts. They're regionally distinctive. You know, if you have a very low relief platform, it gets down to sea level. It only has to subside a little bit before the whole thing is covered by the marine environment. So these individual Chert units, often just a few meters thick, can be traced over tens of kilometers from one side of the belt to the other without really much signs of change. But here and here and here, and all of these are very distinctive Chert units. And again, they represent sedimentation over an enormous period of time, 200 to 300 million years. But by and large, they're very thin. The thickest one up here is one where there's been a lot of search for evidence for early life. It's called the Buck Reef Chert, and it gets up to about 400 meters thick. But all of the others are generally less than 30 meters thick. Many of these thin sedimentary layers include layers of fall deposited in current worked pyroclastic deposits. This is actually ultramafic or komatiitic ash that's being mixed with biogenic material, carbonaceous grains, and deposited by currents. The surfaces, if we could have looked at them at that time, would have looked like some of these intertidal flats or down to relatively deep environments, hundreds of meters, but really flat surfaces, covered mostly by organisms getting inundated or covered, blanketed at times by pyroclastic eruptions. Modern microbial flats, we have good reason to believe that this is not an inaccurate rendering of what it looked like back at that time as well. Absolutely just black goo and or microbial structures. Here's what the rocks look like. They're either solid black cherts or black and white banded cherts. The white stuff is just absolutely pure silica that was probably deposited alternating with these black chert layers, or at times actually self-segregating from the black chert sediments. And in thin section, here's a millimeter thin section, you can see these just lovely draping microbial laminations, particles of microbial mats and other things being ripped up. And we suspect these represent the existence of early microbial communities. I'm not going to talk about this sort of stuff the whole talk. I'm just laying the groundwork to sort of tell you what the basic architecture and environments were like, and we'll get into the meteorite stuff here in a few moments. So for nearly 300 million years, the Barberton area existed as a volcanic platform accumulating thin sedimentary layers during periods of volcanic quiescence. We would suspect that most of the geologic time is tied up in these sedimentary layers, not in the volcanic layers, because the volcanic rocks, especially the komatiates, came out very fast. Here's 3.5, 3.4, 3.7 kilometers of ultramafic lavas that has one 10 centimeter thick sedimentary layer in it and no interflow alteration zones. So they came out so fast that these ultramafic lavas, composed largely of olivine and other eminently weatherable materials, never weathered at the surfaces and had absolutely no materials deposited in between flow events. So this must have come out essentially as one giant burp, even though individual flow units are as thin as 50 centimeters. And they get up to several meters thick. But these eruptive rates were very high. So most of the time is tied up in the surfaces that mark the tops of these units and in the thin sedimentary layers that accumulated on top of them. After about 3.24 up here, the area was uplifted and became a site of deformation and mixed pyroclastic and epiclastic sedimentation, which is the fig tree group. In 1986, Gary Byerly and I, and again with a larger crew in 1989, recognized the existence of layers of sand-sized spherules within this sequence and in similar Archean rocks in the Pilbara belt of Western Australia. We interpreted these to have formed by the quenching of liquid silicate droplets. We identified 4 layers, 2 that are very close together within about 5 meters of one another up here, which we called S3 and S4, 1 down here at the boundary, S2, and 1 down here, 3472, which was called S1. These layers, again, range from about 347 to 325 billion years old. in the Barberton Pilbara belts were interpreted by us to have formed by the condensation of clouds of rock vapor and liquid thrown up by large meteorite impacts. Lava fountains represent another way to form large amounts of liquid silicate droplets, but for reasons which I'll discuss, we didn't favor this origin. And here's in thin section what some of these droplets look like. These are the Archean spherules from Western Australia, which were actually the first ones we found. The spherules beds often occur as 0.2 to about 5 meter thick layers of coarse clastic material within sections otherwise dominated by very low energy, probably moderately deep water conditions. So here are these fine black carbonaceous cherts here, and here's a bed of gritty sand-sized material sitting in the midst of these quiet water deposits. This is one key that we use to identify them. We're out in the field. We're always looking for anomalous, coarse, sandy beds in the middle of sections of sediment that was otherwise deposited under very quiet and usually relatively deep water conditions. The spherules beds often contain spherules, which you can't see here, unless maybe this is one up here, as well as chert and volcanic fragments ripped up from the underlying greenstone belt rocks. So these are big chunks of angular chert that have been ripped up, and all of this green stuff is altered komatiite that has been ripped up from the immediately underlying volcanic sequence. This is S2 that sits right at the volcanic sedimentary or clastic boundary. And most of these beds represent rather high energy events. The high energy events represented by the spherules beds within otherwise low energy environments of deposition are thought to have been tsunamis or major wave and current events generated by the large impacts. And one can see large scale cross-bedding and coarse grain sizes in here. Underlying and overlying beds are very fine grained carbonaceous chert deposited under very low energy quiet water settings. In other areas, the wave or current events associated with spherules deposition did not occur, and layers of pure spherules accumulated. This particular bed right here, consisting almost exclusively of pure spherules, this is a nickel for scale, is 35 centimeters thick of pure spherules, not current or wave deposited. So it's just a fall deposited layer that rained down 35 centimeters of spherules. There's been almost no compaction in these rocks. They were silicified very early, and so it preserves textures and features very well. Spherules bed S1 in the Warwoona group in Western Australia. This is the first one we discovered. The spherules display a variety of internal quench textures, some concentric structuring, and in one instance here, a welded form, giving a dumbbell shape. But you can see these various crystallite shapes in these spherules, which led us to infer that they form by the quenching of liquid silicate droplets, not merely liquid silicate droplets, but often in the same bed, droplets of different compositions. Because you can see that while these are obvious, most of the background also consists of spherules, but now they're composed of pure SiO2. So whatever their composition originally was, it had no alumina in it. Whereas these had alumina, and so we get micas and oxides that give us these various tones and colors. Here is that same bed, slightly different view from Western Australia. You can see more complex shapes where particles have welded together, and again a variety of internal microcrystalline quench type of textures. Again, same thing, these Jack Frost-like feathery quench crystallites. A barred crystal, probably originally olivine. This is spherules bed S3 from the Barberton belt. This particular part of this bed consists of spherules that get up to about 4 millimeters in diameter, composed now almost exclusively of quartz. It's bimodal. There's a population of small spherules here, some of which have been slightly squashed, that are composed entirely of chrome-rich mica. So we've got a bimodal population of spherules here. In that same bed, about 50 centimeters higher. The composition of the spherules has changed. Actually, all of this light seemingly matrix that these spherules seemingly float in is also made up of spherules, but it's pure silica spherules that have been welded together. And then there's this variety of mica-rich and oxide-rich spherules that make up the remainder, some of them with what were open cavities in the center. Here are just some of the varieties of spherules in that bed S3. Again, you can see barred textures in some. It's really hard to see, but these little sort of dendritic, funny little things here, that's chrome spinel, quenched chrome spinel that has formed a skeletal crystallites, again, characteristic of quenching, barred textures, various types of fibroradial textures, macrolitic textures. Again, all in the same rock, all mixed together. Very different compositions of material, all in the same spheruleal bed. Some more from that bed S3. And again, you can now see the silica spherules that form the matrix to these. We concluded that these represented impact layers because the particles were spherical and displayed internal quenched crystallites, indicating that they probably formed as liquid silicate droplets. There were heterogeneous composition in individual beds, telling us that this was not just something like a lava fountain or a volcanic eruption, which would have provided spherules of relatively uniform composition or droplets of relatively uniform composition. The beds are of regional extent and not directly associated with any other volcanic rocks. There's no indications of volcanic eruptions coincident with these beds, and the spheruleal beds, many of them, but not all of them, can be traced across much of the Greenstone belt, indicating they're of regional extent. So it's very difficult to get this as just accumulations around a lava fountain. And these have anomalously high iridium anomalies. Here's a couple of examples here. This is iridium content in part per billion. It's on a log scale. This is some stratigraphic sections in meters. There's one spheruleal bed here, S3, and you can see it jumps up to about 80 or 90 parts per billion iridium. This one goes up to 100 parts per billion iridium. Remember, the KT boundary layer spherules are about 6 to 10 parts per billion. Okay. Chondritic values are about 600. Here's iridium in parts per billion in the Barberton spheruleal beds. Ranges depending on whether they've been current worked. If they've been current worked and mixed with other debris, then of course the iridium content goes way down because there are very few spherules. If they're relatively pure spherules, they tend to be high, but you can get pure spheruleal layers that show no chrome spinels and no little or no iridium. Here's chondritic values, and if you'll notice, there are values in these spheruleal beds that are in excess of chondritic. This does not represent some super iridium-rich meteorite or anything else. It simply reflects the fact that you have taken this bolide material, you have melted it, you've condensed it, and probably in the course of condensation and crystallizing, the iridium has been fractionated into certain parts of those melts and condensates, and then perhaps later by hydraulic processes concentrated the denser spherules to get iridium values greater than you would have gotten in the original chondrite. The spinels in these deposits, abundant spinel is really common only in S3. Many of the spinels display skeletal quenched morphologies, unlike those in associated komatitic flow rocks. The spheruleal spinel is significantly enriched in nickel relative to terrestrial spinel, a feature common to impact-produced spinels. Most of the spinel is chalcophile spinel enriched in nickel, cobalt, vanadium with minor amounts of lithophile, and magnesium and zinc-bearing spinel. Iridium and chromium, which these very high values of iridium, appear to be contained within the spinels. Okay. Well, 1989 to 1990, a number of geochemists who have worked extensively on impact layers reinterpreted the spheruleal beds as a product of volcanism and metasomatic alteration. Okay. They suggested the IR contents were too high in some of the beds, well above chondritic values. Again, we're not looking at pure bolide, we're looking at condensates and fraction materials that have been fractionated by sedimentary and hydrodynamic processes as well as during condensation, so we don't view this as a significant problem. Some evidence of IR diffusion around spherules beds, that is, IR migration over short distances, suggested to them that the enrichment was a metasomatic effect. They never did explain why only the spherules beds were enriched in IR and not any of the associated sedimentary layers. IR is locally correlated with arsenic and other hydrothermally carried elements, suggesting that to them it was probably hydrothermal in origin. So they suggested the spherules are probably of volcanic origin with post-metasomatic platinum group element enrichment. And they showed a chart of iridium versus arsenic and showed there was a direct correlation suggesting it was hydrothermal. Unfortunately, the samples where these guys collected were taken from a gold mine. Okay? Now, gold is a platinum group element, I believe, and if it's been metasomatically introduced as a gold ore, you might expect a little bit of mobility, okay, of platinum group elements. So this was not the place to do a study like this. Finally, in 1999 and again in 2003, it was shown that the chromium in these had isotopic values that were extraterrestrial. That is, terrestrial epsilon chromium 53 had terrestrial values all lie right along a normalized line of 0. Chondrites lie off of this line in negative direction. The spherules beds all had values S1, S2, S3, and S4 had values that depart from terrestrial values. So this sort of satisfied a lot of the geochemists and confirmed the impact origin that had in fact been correctly interpreted 15 years earlier based on field and petrographic evidence. So purpose here is to show you that we're talking about beds that are in fact related to impacts. We're not talking about volcanic features. It's not an open question anymore. Even our detractors have now written a paper summarizing the evidence for early Archean impacts and agree that these are impact layers. It just kept us from getting any grants to study these for about 15 years. Several interesting features of the Barberton spherules beds. Where the spherules have not been reworked by currents or tsunamis, the bed consists of 20 to 35 centimeters of pure spherules. The KT boundary spherule layer is less than 5 meters thick in fall-deposited sections. I mean, these are big accumulations of impact-produced materials. The iridium contents, especially of S3, were not reworked or high, generally 100 to 600 parts per billion. Chondritic values are generally 500 to 700 parts per billion. KT levels are about 6 to 10. Energetic waves and or currents accompanied spherules deposition over most areas, probably reflecting tsunamis that were shallow water waves to depths of several hundred meters. And in many, many sections, we have real evidence that they just tore up the bottom at water depths that were for prolonged periods of time, felt no wave, storm, or current activity. In the fall-deposited layers, virtually all of the particles are spherules. There are no known breccias and little or no coarse ballistic debris. The sites of deposition that we have are all distal from the impact sites. Here's the KT boundary layer, okay, in a fall-deposited section in northwest Mexico. There is the KT boundary clay. Again, here is a spherules fall-deposited layer, just part of it from one of our beds in Barberton. Subsequent to confirmation that at least 3 of the original 4 spherules beds were of impact origin through chrome isotopes. There was too little chromium in spherules bed 1 to do the isotopes on it because that bed has everywhere been ripped up by the tsunamis or currents to get enough CR. At least 4 additional spherules beds have been discovered in the Barberton belt. Detail mapping has shown what a profound effect S2 and S3 had in the regional Barberton Greenstone Belt depositional and tectonic systems. And S1 has been dated at 3472 and correlated with a spherical bed in the Pilbara block of Western Australia of exactly the same age. That is, we have now a correlation between South Africa and Western Australia in terms of this bed. Yes?
At the time of these impacts, how far was Western Australia from South Africa?
Well, that's a subject of some debate. A lot of people like to put them close together because the stratigraphies are very, very similar. It's a little hard to say because they seem to have been part of a supercontinent or Gondwana land, as late as the late Proterozoic. The question is how much moving around they underwent between when they were assembled into Gondwana land and when these belts formed. It's 200 million years or so in between those events. So either they were very close together and have similar histories, or maybe the early Earth was much more characterized by sort of global events that left very similar volcanic and tectonic patterns on a global scale. We don't know the answer to that. So here are the original 4 spherical beds that we identified. Here are the new spherical beds we've identified in the belt. These have not been written up and described, so I've just assigned tentative numbers to them: 5, 6, 7, too close together to separate, 8. And 9 is not actually a spherical bed, but it appears to be maybe a little bit more proximal type of unit that reflects an impact. These are also all very thick spherical beds. Were composed largely of spherules, and virtually all of them also, in most outcrops, show evidence of high energy wave or current activity. Okay, our work also suggests that especially S2 and S3, and we haven't studied the others as much as we've studied these two, had a really profound effect on the depositional system. First of all, these 2 spherical beds occur right at, or very close to, the transformation from the thick volcanic succession down below to the orogenic clastic succession up above. And in most of the outcrops, you can walk through a thick section of fine black cherts like those occur through out the lower part of the sequence into the spherical bed, and within a few centimeters of the top of the spherical bed, you're into clastic sediments and iron formation, marking the fig tree group, and forever the world changes. And it changes right at that boundary where that spherical bed is at. Spherical deposition was accompanied by belt-wide fracturing of the upper 50 to 100 meters of the underlying rock sequence and downward injection of soft carbonaceous surface sediments that locally include loose spherules into the fractures to form what are now chert dikes. And I'll show you some of these. We know that these formed almost exactly at the time of spherical deposition because there are loose spherules that are carried down into the dikes, but the overlying sandstone, the overlying clastic material that followed spherical deposition, is none of that in the chert dikes. So it didn't make it down. So it formed right then, sucked the spherules down, but the overlying sediments hadn't accumulated yet. And there's widespread shallow faulting and block rotation of this upper damaged part of the sequence. So here's a map of a small area. The fig tree rock contact runs right along here, up like this, faulted down like that, like this. And this is just an absolute, I've just drawn the bigger chert dikes. They come up to, in many places, right to this fig tree rock contact, but never above it. Okay? They originated in a black chert layer that is the upper 10 meters of the underlying Onverwacht materials. This is a black chert sequence, and they come out of a layer that was at the time unlithified right at the top of that. And you can see there are a number of places where there are spherules that have been sucked down into these chert dikes. Here's what one of those chert dikes looks like. They range from small things, this one a few centimeters across, to dikes that are 8 or 9 meters across, so they get very large. Now, this is a kind of a strange one. I'm flying here in a little 2-man helicopter. I'm looking down almost perpendicular to bedding. The bedding is dipping on this hillside steeply toward me. And you can see here is a barite layer The fig tree Untitled contact runs right here, and then along here, and like that. Here's spherical layer S2. Right against that contact, there are then black cherts and other black cherts in a thick sedimentary sequence that is at the top of the Untitled group. Spherical bed is right here. All of these things I've drawn in here are chert dikes. They come up right to that contact, but never cross it. And if I take off the lines, you can see how what this chert dike complex actually looks like. I mean, the crust is really shattered here, and all of these things that run up like this, because bedding is going across like this, are chert dikes that have been injected downward at that point in time. So they contain spherules, but they contain none of this overlying material in the fig tree group. Here's another view of a hillside from quite a ways off. These are nice oak trees here. And you can see some big black chert dikes. Fig tree Untitled contact is right about there. Okay. Big black chert dikes coming down here. Here's another one here. Here's a big one that comes down. Here's some huge ones up here. But look at all of these tiny fractures. All of those vertical things are chert dikes that are cutting across stratification in the upper part of the Untitled group. I mean, when I say shattered, it was literally shattered with hundreds of these dikes injected downward. And in our wanderings around the countryside, we've found places all over the Greenstone belt where spherules have been sucked down into these chert dikes and where these chert dike complexes. So this contact is regionally marked by extreme crustal shattering. Here's a good example showing this light gray is the top of a giant chert dike that extends downward for about 100 meters or more. It has locally been squeezed up into parts of the fig tree group, a big rotated block here, but by the time you get up to this level, everything is annealed over and there's no more deformation, no more faulting. And here are some huge spherical masses that have been sucked down into this chert dike. This bed is everywhere undisturbed, and we think is a second impact layer of spherules. There are two spherules, beds S2 and S3, that occur in this section. Here's another indication of deformation, although not shown on this diagram. There's a spherical bed right through here, right at the top of the black cherts, a little bit laterally. Immediately following deposition of these black cherts in that spherical bed, you got faulting that uplifted locally blocks that produce thick fan delta accumulations of conglomerate, clastic material, and by the time you get up to this point in the stratigraphic section, everything is back to fine-grained sediments again for a while. So there's really a major episode of crustal disruption, fragmentation, block rotation, and a short episode of clastic deposition before we're going back to mainly tophaceous sediments for a while. So based on IR abundance and thickness of spherical beds, the bolides responsible for S2, S3, and S4 have been estimated to be 20 to 50 kilometers diameter. That includes the volume of material and the amount of IR fluence that we see in these layers. The large amount of distal crustal shattering associated with S2 and S3 suggests that these were produced by very large bodies, perhaps towards the upper end of this range. The ubiquitous erosion of the seafloor by impact-generated tsunamis that accompanied deposition of all of the spherical beds in waters down to 200 to 300 meters deep suggests that they represent a population of very large impactors. These tsunamis probably circled the globe perhaps several times. The sizes of craters formed by S2 and S3 bolides were probably between 350 and 900 kilometers in diameter, assuming that the bolides were 20 to 50 kilometers across. This is based on a calculator by Malash and Bayer. 350 kilometers is pretty close to Mare Nectaris down here, a little bit smaller than Mare Crisium here. 900 kilometers, a little bit smaller than Imbrium, a little bit larger than Serenitatis, just about the size of Mare Orientale. So we're talking about huge impacts that probably formed enormous basins on the Earth at the same way things were forming on the Moon. And if we look at relationship between bolide diameter and interval between impacts for younger geologic time, bolides about 10 kilometers in diameter, like that at the KT boundary here, have a recurrence interval of about 100 million years. Okay? The 20 to 50 kilometer diameter bolides responsible, we think, for the Barberton spherules beds have a Phanerozoic recurrence interval of 1 to 10 billion years, depending on whether you're at the larger, based on present impact rates. Okay? Rocks of the Barberton belt show at least 8 major spherules layers over an interval of about 250 million years. Not one large impact every 1 billion to 10 billion years is implied by current impact rates. So models of the terrestrial impact flux suggest that impact rates 3.5 to 3.2 billion years ago were not substantially different from those today. Results clearly inconsistent with the implications of these beds. That is, if this is a present day rate, the sort of cool Earth curve derived from lunar cratering rates shows the late heavy bombardment here, 4.0 to about 3.8 billion years ago, accretion tailing off very quickly here, and at 3.5 to 3.2 you have rates that are essentially the same as they are today. If you look at an exponential decay curve, they too show a little bit more of a tail, but by the time you get to the age of beds we're looking at, you're still down at present-day impact levels. There are at least 2 clusters of large impact event beds in the Archean geologic record. The one here in the Barberton belt, which spans a time interval of about like that, and includes 8 beds that we know of. And again, all of these beds are thick beds. We really haven't got down to identifying thin beds yet because they don't stand out as well in outcrop. And 2.7 to 2.5 billion years in age, which are impact layers that occur in the Hammersley and the Transvaal iron formations. Now, these may represent clusters. Okay, so are there clusters of impacts? But it also happens that these represent environments of deposition that are relatively deep and relatively quiet and would preserve impact layers. There's virtually no rocks between 3.2 and 3.0 billion years ago, so there's nowhere to hunt for an impact sequence. And the rocks from about 3.0 to about 2.7 or 2.75 are mostly craton cover sequences. That's the earliest cratonic cover that we have deposited on top of the Kapval and the Pillbar craton. That's all right. I would add that there are greenstones in Canada of this age. The greenstones, however, in Canada don't contain any known spherules layers. The spherules layers for these are present in craton cover iron formation, which is very quiet, very deep, very continuous environment that would allow the preservation of spherules layers. So there are 4 or 5 layers known in this interval. There are at least 8 known in this interval, and none known in here, but it may be a matter of preservation. So the question is, the number of impacts, the impactors we see in the Archean just don't fit the current notion that the impact rate in the Archean was no different than we see today. There are just too many big impacts. Every one of these impact layers that we've discovered in the Archean is bigger than, I think, almost anything, especially distal layers, that we have from later geologic time. I mean, something was going on. Either we had a series of clusters of large impacts after late heavy bombardment, gradually probably tailing off in number and size, or we had a much more gradual decline in the overall impact rate. That this apparent clustering is due to a matter of preservation. And potentially, one could even extend this back in some fashion like that. But the point is, there's a problem. So the results of our Barberton studies suggest the existence of at least 8 major impact layers deposited over an interval of about 25 million years. These layers record a level of large impacts well above that predicted by current models of Archean impact flux. These results suggest that substantial modification of the early impact history of the Earth is needed, and possibly that following the late heavy bombardment, the impact flux gradually declined until 2.5 billion years ago, the end of the Archean. Thank you.
Jill, hold on a second.
So the story of the late heavy bombardment, as I understand it, is based on cratering records on the moons and things like that. How does this new look? How is it consistent with that cratering data?
It's not consistent with the notion that there was that things just there. We can't look back in Barberton to the late heavy bombardment. Our good record starts about 3.5. Okay? If you believe the interpretations of the cratering record on the moon, the impact flux on the surface of the Earth, numerically modeled to fit the surface of the Earth, is about the same at 3.5 as it is today. It doesn't fit with what we see in the geologic record. So there's a clear conflict. And so either there were further clusters of impacts following late heavy bombardment, or late heavy bombardment is a window that we can see on the moon, and for whatever reason, later impacts either aren't there, or are masked by the earlier large ones, or they've just got it wrong. All I can say is, all I can do is read the geologic record 3.5, 3.2, and there are a heck of a lot of very large impacts that would have been basin-forming impacts had those things whacked into the moon at that time.
Yeah, the lunar record is mostly from the Lunar Maria, where you've got these Apollo samples, all from kind of around the same place. And then they count the number of 4-kilometer diameter craters atop what they think are surfaces of a given age. I think it's, there's lots of room for analyzing that, but if you just plot them up, it doesn't look like the impact rate is declining to zero quickly. It looks much more like what you get than it does. If you just take it naively. Another one is Vesta, where you have these eucrites, howardites, and diogenites, which come from the asteroid Vesta, and they're scattered from 3.4 to 4.1. Okay. They also don't have that rapid fall off that is popular among the catastrophists.
Catastrophes. Yes.
You're getting much higher iridium concentrations in these layers than in the KT boundary.
Yeah.
Any explanation why there would be, does it have to be a more iridium-rich impactors, or different mixing with the crust, Earth's crust?
Well, you might have had, the bolides have been modeled based on the chromium isotopes as carbonaceous chondrites. Alexander Shikulyakov has done that work, and to my knowledge, no one has contradicted it yet. They often seem to be accompanied by the fallout of fine komatiitic ash, a dust. Okay, so they impacted into basalts and komatiites. We've modeled, at least for maybe S4 and S3, the composition of the target rock. And the target rock is always mafic to ultramafic, and it involves some komatiite and some basalt. But the komatiites would certainly increase the overall flux of chromium up into an impact vapor cloud, which would consist mostly of target rock and bolide. The thing that we have wondered and proposed and actually tried to do a little bit of a study of is when you get, if it's a rock vapor cloud and you start condensing out the most refractory components, iridium may well go with those initial most refractory components. And so there would be a fractionation of iridium from other components in the course of condensation, and then it'd be locked in then for crystallization. So it may well be, I mean, if we plotted, say, just for one bed, if we plotted all of the values we got and included all of the layers where its current worked and some of the relatively pure layers where there's relatively little iridium, and some of the graded layers where there's lots of iridium here and little iridium up there, we'd probably find that it would average out into much lower values, something more like the KT boundary. So there have probably been quite a number of fractionation factors, plus a slightly greater amount of iridium to start with because you're hitting commodioids. But you've probably gone through a number of fractionation processes that have allowed concentration of iridium over not only terrestrial target rock, but locally even chondritic values. But I think it'd all average out to be, a good mix of target rock and bolide.
What are the oldest bacterial mats that you're seeing in this area?
The really lovely one that I showed you there is about 3.4. Okay? We can find similar sorts of really nice microbial structures back to about 3.482. That's based on zircon dating, and it's at the top of the Kamadi Formation. Down below that, the rocks, as you go down deeper in the section, they've been influenced by tonalitic plutons that have come up and invaded the roots of the belt. So we can neither hunt for spherules beds nor well-preserved microbial structures in the lower part of the sequence.
So what you're saying is that you see life all the way until the bed's now is no longer undisturbed and there's been processing.
Well, these aren't undisturbed. They're all standing on end, and they've been very heavily deformed. But in a lot of the Chert layers, there's been no penetrative deformation, no shear. And there was very early silicification. So like those microbial mats, the carbonaceous particles weren't squashed at all. They were just there.
So you do think that life is suddenly appearing then?
No, I don't think it's suddenly appearing. I think as you go down in a sequence, you get into layers that are metamorphosed, and there you can't find morphological remains that look like life. But above that sort of metamorphic boundary, which is marked at the top of that 3.5 section of commodioids, that's where the first really nice, fresh, unmetamorphosed sediments appear. There's plenty of carbonaceous matter in those. So I think we're not looking at the beginning of life or any lower boundary. We're just looking at the preservational boundary. I think it was well before then.
Just for a comment on the previous question, and in fact, I think it's established that the impacts of the size you're talking about are not sterilizing for the planet. So that, yes, you'll certainly disturb the ecosystems like crazy, but life itself will continue. One of your lines of evidence for interpreting the effects was the transition from the to the sedimentary deposition, from the volcanic deposition.
Yeah, that sort of appearance, the
Then that they all seem to line up that way.
Orogenic sequence, yeah.
But the question I had was, could that be a preservational effect? Because if you continue volcanic deposition, would that have destroyed these and you wouldn't have seen them or made them otherwise difficult to find?
No, because within the spherules that are down in the volcanic section, there's been plenty of pre-spheruleal and post-spheruleal volcanism. It has no effect on the spherules. Really, the only thing that acts to disrupt and destroy these fine textures is if you get penetrative deformation, if you get a shearing that produces a foliation, and we can see that. Golly, I didn't have a slide. I meant to put that in. I have a slide from an area near one edge of the belt where it has been sheared, and you can see these elongate spherules. They do get stretched out, and then you'll lose them. So you really have to be away from schistosity. Thermal effects aren't so bad unless you recrystallize your chert up to a really coarse quartzite, and then you'll lose original structures. But some of these layers have been cooked to 300 degrees, 350 degrees centigrade with no strain, and you can just see these structures down to 10 microns or less across with no problem. Let me bring up one issue, and Dave, maybe this is what you're going to ask about. I don't know. Martin Brazier, there's been some discussion about the organic matter as whether it's biological or not. And a number of people have demonstrated that you can produce simple organic compounds by reactions with ultramafic rocks, water and ultramafic rocks, carbon dioxide and things. Now come these simple organic compounds, and it's even been suggested that you can produce some simple filament-like squiggly sorts of masses of carbonaceous matter through abiotic processes. But I don't think anyone has produced anything like these mat-like and carbonaceous particle structures through abiotic processes. There's just there's so much of this carbon. It is just distributed in huge volumes through enormous sequences of rocks, far, far away from any evidence for vents or other sorts of exhalative sites out in the world ocean. Throughout any time there's a sediment that is not being clastically deposited or chemically dumping out, or you're burying the surface in volcanism, you're depositing organic matter. And I think these oceans were just absolutely teeming with microbial life, and it was accumulating virtually everywhere. Another good evidence that this stuff is not abiotic is that in the study a student of mine, Mike Tyson, did on the Buck Reef Chert, we looked at the distribution of mat-like layers like I showed up there. Mat-like layers are developed. There's a nice deepening upward sequence. This volcanic surface subsided, went down through a little evaporitic zone, some evaporitic coastal basins, and then into a shelfal sequence, and then into a deep water sequence that eventually became iron-rich. As you go up through this succession, there's a point in the succession where large beds of broken up clasts and breccias, which we think are storm generated, they disappear. We think you've reached storm wave base. And above that, there's just no signs of currents, no signs of transport, no signs of storm. And that's also the end of in situ microbial mats. Everything above there in these cherts is very fine organic carbon deposited as very fine detritus. And we think that what you've reached is not only storm wave base, but that is almost, in modern oceans, that's roughly coincident with the bottom of the photic zone. That the reason you're not getting any microbial mats or mat-like structures below that is because you've got to the bottom of the photic zone. So all of the carbonaceous matter is being transported in the water column and settling out. That's another thing. It makes us think that these were living organisms because they are environmentally controlled. That wouldn't be the case if this were just abiotic material floating around in the world's oceans. You wouldn't have that type of control. Sorry, Dave.
Okay, well that's good you did that because this changes the topic a bit. 20 to 50 kilometer diameter bolides are excavating the upper mantle. It would seem to me you should see some consequences of that, either in hydrothermal activity, because you can imagine you'd be setting up a hydrothermal system that could last for hundreds of thousands of years. And then, of course, volcanic outpouring. Other people have linked volcanic outpouring to impacts. I'm thinking of KT, the Deccan traps. I mean, by comparison, this is an enormous set of events you're talking about. Do you see anything that's consistent?
Well, if you'll notice that the distribution of commodioids in this sequence is pretty, they're on, they're off. The biggest unit is this commodity formation down near the lower part of the sequence. I think it's very possible that some volcanic episodes were triggered by these. Now, key thing to remember is that all the deposits we've seen so far are distal deposits. And it kind of makes sense because if we get whacked by an big impact right here, our stuff would be gone. So I think the only place on Earth we're likely to preserve these types of units relatively pristine until later tectonic deformation would be where the impacts themselves aren't hitting. And so what we see is a lot of distal material, perhaps some major mafic or ultramafic volcanic episodes triggered by the events, but we're not close enough to the impact sites to suffer any of the disruption and devastating events that we would see. And I think you're absolutely right. Probably did excavate down to the mantle, and it may well be that if we analyze some of these thin, what look to be commodiotic ashes that accumulate right on top of some of the spherules beds, that we'll find some unusual components that aren't in normal volcanic commodioids. That might tell us, yes, here we're looking at virtually 100% melting of mantle material instead of a 70% melting of mantle material. But that's a subtle difference, and if it gets diluted by other things, we may not be able to tell that. But I think you're probably right. These were big, yeah. The ocean was essentially invisible. They just went right through it, and perhaps the crust as well.
Okay, so I know you've been associated with a lot over here.
Oh, okay.
Sorry, I know you've been associated with a lot of high temperature estimates from the Archean, from oxygen isotopes and Chert, but I can't remember where they are in the stratigraphic sequence. I was wondering if you could talk about them, whether they're near these impacts or whether they're a long way away and a totally different issue?
Well, again, remember, most of the impacts that we think we can identify are distal. There's one, I referred to one S9 layer that I said wasn't a spherical bed, but it may be an impact layer. That's a layer of felsic volcanic material. It has some big blocks of komatiite that are maybe half a kilometer or a kilometer long. And near the center of this thing, if you look on the flanks, there are two big kilometer-long blocks of komatiite that are absolutely upside down. They've just been flipped over like that. Now, that could be by a particularly violent eruption, but boy, that would be a violent eruption. The thing that I'm acquainted with most that flips big blocks of things upside down are impacts. Now, we haven't studied this enough. We've got it mapped out now, and so I need to sit down and do a little bit more with it. But that may be an impact feature. That may be getting a little bit closer to the impact site. But that would probably be a smaller one. But other than that, we're in distal environments. Yeah, I was involved with Paul. I'm actually the co-author on that paper that Paul Knaut wrote. And then I've done a sort of a thermal history of the Archean Earth based in part on the oxygen isotope data. I'm a fan of high temperatures. But I think they were high temperatures, and Kevin and I know, and Norm Sleep have some real disagreements here, but I think they were high temperatures that characterize the whole surface of the Earth, at least during the deposition of these rocks. And caution you to be very careful, even during the Archean, of finding a sample or reaching a conclusion based on one spot and saying, well, that's what the Archean was like. You know, the Archean is a long interval of time. And there were probably changes in conditions across the Archean as radical as we see across the Phanerozoic. So I think that the mere fact that we've identified relatively high temperatures at one point doesn't necessarily mean there were high temperatures at all points. But I don't think these impacts are large enough that there could have been a significant transitory effect on surface temperatures. Not big enough to boil the oceans, but maybe big enough to boil off 50 meters of ocean surface water. To favor the survival of thermophiles, so we say. But not enough to boil the oceans. But those temperatures would have been transitory. And I think the things that we see recorded in oxygen isotopes are probably much longer term effects. Unless we just happen to get a Chert layer deposited during a transitory high temperature stage related to impacts. And again, I point out that we've only found these big, thick beds. We haven't gone to any of the Chert layers that we think accumulated under very low. Well, we did one under very low sedimentation rates in deep water and done iridium profiles down them. We did that with one, and we got a number of iridium spikes in the 5 meters that we went across. But it's very difficult to rule out potential komatiitic ash unless you get really high iridium spikes and things like that. But surface temperatures, I'm not sure there's any relationship between the oxygen isotopes came from these same sections, just not from the impact layers. So they were right there, same place. But it's not clear that those have any relationship to impacts.
Let's actually cut things off here. This sounds like you could keep going forever, and I encourage you to continue the discussion up here with the speaker afterwards. But for now, let's thank Don again for a very interesting talk.
Thanks a lot.